Alright, hey guys, what's going on? This is my second video for the actuarial P exam textbook. So today we're going to be looking at probability. I guess first I'll kind of just do a quick recap of the last video, which was probability, spaces, and events. So if you'll remember, we went over a bunch of different definitions. There was sample points, sample space, which is a collection of all sample points. There were disjoint events or disjoint sample points, which are just sample points or events that do not overlap, and a collection of them is called a partition. And if you think of it like a jigsaw puzzle, each piece would be a partition of the sample space. So like, you have a sample space here, and then you have it chopped up into a bunch of different non-overlapping pieces that would make each of these disjoint, and they form a partition of the set, which we could just call S. And we also went over events, and we used the example of the die, like a six-sided die, where you can throw an even number, or it lands on an even number, so then your only sample points would be 2, 4, and 6. Or you throw a number less than 4, which would be 1, 2, and 3. And then we also looked at union of sets or union of events, and which is the collection of all events or sample points, the collection of all sample points in a set A or a set B. So if you have A and you have B here, then A union B would be all of this. And for intersection, you could have the same A and B. A intersect B would just be this. So this is sample points that are in A or in B, which means it would be this entire area. The intersection is sample points that are in A and are in B. So that means that would only be that middle part right there, because they are in both A and B, which is what intersection means. Intersection is and, you can think of it like that, and union is or. So the language is very important here. But today we're going to look at probability, and I'll start with a definition or two. So if we're looking at a finite set of countable points, then it looks like this. You have A1, which is the first sample point, A2, all the way to A sub n. And this is finite, and that just means that you can count each individual point and then reach like a final sample point. So this is finite. But if it were infinite, then you'll notice I didn't put an A sub n, and that just means that this goes on forever. Of course, infinity, infinite, infinite. So this is a finite set, and this is an infinite set. And remember, finite is denoted by the A sub n at the end over here. Okay, now the probability function, or whenever you're looking at probability of something, anything happening, then it has to satisfy a couple things. So the first thing it has to satisfy is this. And what this basically is saying is that the probability of something happening has to be equal or greater than 0, or equal or less than 1. So like, if the probability of something happening is 0.2, okay, that makes sense because it's between 0 and 1. Or it could have a probability of 0, which means it doesn't happen, that also makes sense because that probability can be equal to 0, but it can't be greater, it can't be less than 0 and it can't be greater than 1. So you can't have like a 1.2 or a 120% chance of something happening. That would just be 1. Like 1 or 100 is the highest that it could be. It can't go past that, and it can't go behind, or it can't be anything less than 0. So that's what this is saying. And the second thing is that the sum of all probabilities has to be equal to 1. So if you have 3 things happening, let's just say 3 things, or I guess we'll make it simpler. If you have 2 things happening, 2 events, then the probability, when you combine or when you add the probabilities of those 2 things, I guess plus also anything like the sample space outside of those 2 things, it has to be equal to 1. So I guess just for simplicity, we'll say it's only 2 things. Let's say the probability of thing 1 happening is 0.2. That means that the other thing, event number 2, has to be 0.8. So if A doesn't happen, then B has to happen, and if B doesn't happen, then A has to happen. And when you add those 2 probabilities, they have to be equal to 1. And that's like for all i's, which is a sub I right here. A sub I is just the events happening. So for all i's, which like we were saying with the finite sets, A1, A2, A sub n, for all of these, whenever you add all of these up, all of the probabilities up, they have to be equal to 1 or 100. It just kind of depends on the problem, if you're going to 100 or if you're going to 1, but yeah, it can't be greater than 1 or greater than 100. So again, just the summation of all probabilities have to equal to 1. That's what this is saying. So there are a couple probability spaces, and there's finite and there's infinite. So a finite probability space would be tossing a die, like a 6-sided die. And it's finite, it's countable because there are only 6 possible outcomes. 6. There are only 6 possible outcomes. You either land on a 1, 2, 3, 4, 5, or 6, and that's it. That's like all the possible outcomes. So it's finite, it's countable. But an example of an infinite probability space, it would be like when you flip a coin. Now, you only have 2 sides to a coin. It's heads or it's tails. But you could well, I don't know how realistic it is, but theoretically, you could keep flipping the same coin and only land on heads, and then never land on tails. So yeah, let's say you flip a coin, then let's say you flip the first time, okay, you get a head, you get heads. You flip a second time, heads again. You flip a third time, heads again. And this sample space won't close until you get tails. Hold on, my cat's on my counter. Okay, so this sample space theoretically would never close until you get a tails, but also theoretically you could just keep getting heads forever. And that's why I didn't put a T for tails, signifying that the sample space is finite, because this is a possibility. You just keep getting heads forever. So this would be I guess it's kind of like the simplest example of an infinite sample space. Okay, the next thing that I have written here. Also, all of these notes, I've already done the reading myself, so it's like a very simplified version. I'm hitting on like the important parts. So the next thing is uniform probability function. And that just means that every sample point has the same probability of occurring. So again, a die, like you flip a die, right? What's the probability that you land on a 1? Well, it's 1/6 because there are 6 sides. And every face has the same probability of landing. Again, because it's a 6-sided die, so 6 would be the denominator, right? And 6 is also the number of different outcomes you could have. So we'll say K, and K is just like the general like number of outcomes something could have. So yeah, so the probability of landing on any side of the die would be 6, or 1/6. I mean, you know, you land on 1, that's a 1/6 chance. You land on 2, it's another 1/6 chance. And that's whenever something is uniform. So I guess you could also look at a coin, right? What's the chance you land on heads? It's 1/2, because there's only 2 sides. What's the chance you land on tails? It's also 1/2. And that is what we mean. That is what we mean by uniform probability, where every outcome has the same exact probability of happening. So yeah. All right. Okay. Now we have like 12 rules regarding probability, and there's just, I mean, they're just rules, right? They're just, you just kind of take them as they are for now, but once like I show some problems later, then they'll come in handy. But okay, let me quickly take a look at these. Okay, I need the textbook too. Okay, so I guess for the first rule, the probability of S is equal to 1. This means, what this is saying is that the probability that something will happen in the sample space, like the entire space that we're looking at, is 1. Which makes, like, logically, it kind of makes sense, right? Like, if you do an experiment and you expect something to happen, then yes, something will happen. So that probability is 1, or 100% that something will happen if you conduct an experiment. The second rule is that the probability of the null set is 0. So a specific example here would be like if you threw a 6-sided die and, or like this is the probability of you throwing a 6-sided die and then not having any face show up. Well, that obviously can't happen. Something will always, like, you're gonna land on a face, so the probability of you throwing a die and not having anything show up, like, would be 0. All right. Okay, if you have events that are disjoint, so if A1, A2, A3 are disjoint. Also, I guess I should have made this more explicit earlier, but capital letters mean events, and if they're lowercase, like lowercase a, then that's just a sample point. So remember, events are experiments and they have parameters. Sample points are results from experiments. So if we have events that are disjoint, then the probability of the union of all of the events is equal to the probability of event A1 plus the probability of event A2 plus all the way, which equals the summation of all the events, equals the probability of the summation of all the events. So maybe this will make better sense in an example, but the way I'm reading this is the probability of the union of all of the events is just equal to the sum of the probabilities of the events. I guess I don't really know how to better explain that. Maybe, like I said, I'm sure there's going to be an example where this comes into play, but this just reminds me of being back in college. Like, I don't know, sometimes you would, like in math, the professor would tell you something, and then you just had to take it as it was. I don't know. Oh, maybe people are right. Maybe math is fake. Okay, I'll keep this here for now. Kind of just take a look at it. Like I said, hopefully this makes better sense in an example. I'm also trying to look at the textbook and see if it explains it a little better than I'm doing it. When we have mutually exclusive events and we add the event probabilities, there is no double counting. Okay, double counting, that'll also show up later. Okay. Okay. I will. Hopefully this explains itself later. Or maybe it already made sense. I don't know. Okay. I'll keep going. For any event A, the probability of A is equal. Okay, I already did this one. So for any event A, 0 is less than or equal to the probability of A, which is less than or equal to 1. There's a separation here. So this is what I explained earlier, where the probability of something happening is less than or equal to 0, or is greater than or equal to 0, and is less than or equal to 1. It can't be less than 0, and it can't be greater than 1. Okay. If A is a subset of B, then the probability of A is less than or equal to B. So yeah, like if you have a sample space B, so let's say this circle is B, and then you have a sample space inside of it, which is A, then the probability of A happening is less than, or it can be equal to the probability of B. I mean, yeah, obviously A is a much smaller sample space, so that makes sense why it would be less than B. But A could also, in some examples, be the same size as B and still be within B, and that's why it could also be equal to B. So again, if A is a subset of B, the probability of A is less than or equal to the probability of B. And this is kind of a drawn example right here. Okay, here's where like double counting kind of comes into play. So whenever you're trying to find the probability of something, you don't want to double count probabilities because then it'll make your answer wrong. And I'll show you guys. Well, I'll show you the rule, but I know for a fact that one of the examples I'll show up here is going to have that. Okay. So let's say we have 3 events. So we have A, B, and C. So if we're trying to look for the probability of the union of A and B, then what we would have to do is take the probability of A, add the probability of B, and then subtract the probability of A intersect B. So this is what it means by double counting. So, okay, maybe I could actually draw the example here. Okay. So let's say we have A here and we have B right here. If we're trying to find the probability of the union, and remember that is this entire area of these circles, then we find the probability of A, which would be the entire circle of A, and that's including that middle section, because while yes they overlap, that middle section is still part of A. So again, we take the probability of A, which is the entire A circle, plus the probability of B, which is the entire B circle, and yes, that also includes that middle part. Minus the probability of the intersection of A intersect B. So what we've done before this, what we did was we counted this middle section twice, because remember, we're counting it once for the A circle and we're also counting it again for the B circle. Now we have to subtract it once, and that is what this lets us do. That way we don't double count. That way we don't add this middle section twice like we were just about to do if we hadn't done this. So we're only taking, we're taking one middle section out from here. And now we're only counting each section from each circle once. So the A section, the middle section, and the B section. So, and it works the same way if we have, 3 events. Right now this is only showing 2 events, but okay, what if we had 3 events? Where is it? Okay, so the probability of A union B union C. So again, we would add each individual event's probability. So the probability of A plus the probability of B plus the probability of C. And then now we're subtracting the middle sections because we've double counted in this part right here. So we're subtracting the probability of A intersect B minus the probability of A intersect C minus the probability of B intersect C. But there's one crucial thing that we're missing. This is almost done. So again, what we've done so far is we've added each individual event's probabilities, which means we've double counted in the intersections of 2 events. So we're subtracting A intersect B, A intersect C, and B intersect C, which is similar to what we did here. but and I'll draw this out too to explain it. But now we need to add one more probability back into the equation, which is the probability of A intersect B intersect C. Okay, now I'm going to try to attempt to draw it and explain it. So let's say we have A, we have B, and we have C. A, B, C. So to find the probability of the union of all of these three events, again, we take the probability of A, and that includes the sections where A overlaps with other circles, and I'll use different colors also. So A would be the entire circle of A plus B, which is the entire circle of B, and again, that includes where it overlaps, plus C, the entire circle of C, okay, now we have to subtract the parts where we double counted. So we're subtracting one probability of A intersect B, which is right, it's like right here. I'll show you. Okay. And we're always subtracting once. This section, we counted it twice whenever we added the probability of A and the probability of B. So now we have to subtract one from the equation. So instead of it being black and blue, now it's just black. Okay, we also have to subtract one probability of A intersect C, which is right here, where it's black and it's red. So now let's just make it black, because we're only subtracting one. Okay? And then we subtract one probability of B intersect C. So right here, where it's blue and red, well, let's just make it red. Okay. So, effectively, we have added all three probabilities together. Now we subtract one from each part where two events intersect, which is 1, 2, and 3. But now we have to add in the part where all three intersect, because we haven't counted that part yet. Or we haven't even, discussed it yet up until right now. So, yeah, now we have to add this middle section where, again, all three of them intersect, right there, that middle triangle part, and add it back into the total probability of the union of all three. Oh, I'm sorry. So now what we're doing is we're counting each individual section, 1, 2, 3, 4, 5, 6, 7. 7 individual sections, and we're adding them all together to get the total probability of the union of all three events. So the subtracting prevents us from double counting, and at the end we just have to add once that middle section where all three intersect. I hope that explained it well. It definitely helps a lot to visualize it like this with Venn diagrams, which is what the textbook does. So yeah, that's just this entire equation drawn right here. Okay, so now on to the next rule. Okay, the next ones are a little quicker to understand, hopefully. So for any event A, and so this is rule number 7. So for any event A, the probability of the complement of A is equal to 1 minus the probability of A. Remember that complement means everything not in A. So if we have 100% probability, or just 1, then the probability of everything that is not in A is equal to 1 minus the probability of A itself. Which makes sense, you know, you have A, and then you have literally everything else. And so that is how you would find the probability of the complement of A, would be literally everything else minus the probability of A. And then that's A complement, or the probability of A complement. Okay, for events A and B, oops, for events A and B, the probability of A is equal to the probability of A intersect B plus the probability of A intersect B complement. So I can illustrate this using Venn diagrams. So let's say we have A and we have B. And let's say we only want to find the probability of A, which would be just this circle. And you'll see it's split up into 2 different parts. You have this part and the middle part where they overlap. But if we only want to find the probability of A, then we can find that by adding the probability of A intersect B, which is, again, the intersection, which is this middle part, plus the probability of A intersect B complement, or everything that is in A and is not in B. So what does that look like? Well, that's just this other part, right? Everything that is in A and is not in B. Well, this is obviously not in B, so boom. And sometimes these questions will appear where it asks you to find the probability of only one circle of the Venn diagram, but you know, you kind of gotta like work your way by finding these 2 individual parts first, and then at the end you just add them together. Okay. For exhaustive events B, okay, so this kind of goes back to a previous rule where if you add all of the, remember, exhaustive events is all possible events or outcomes. If you add all of the events together, then you get 1, right? Which is like the total probability. And if they're exhaustive and mutually exclusive, they form a partition, which I already explained with the whole jigsaw puzzle example. Okay, so that, I won't rewrite that. If P is a uniform probability function on a space with k points, and if event A consists of m points, then P, the probability of A is equal to m over k. That's just the uniform probability thing that I was explaining with the 6-sided die. Every face has the same probability of landing. You know, so if you have an 8-sided die, then every face has a 1 over 8 chance of happening. If you have a 20-sided die, every face has a 1 over 20 chance of happening. So I won't rewrite that either. Probability, percentage, proportion, they all mean the same thing. And okay, for any events A1 through AN, the probability of the union is less than or equal to the summation, with equality holding if and only if the events are mutually exclusive. Let me see something. Okay, for any events A1 through A sub n, the probability of the union of all of those events is less than or equal to the summation of the probabilities, with equality holding if and only if the events are mutually exclusive. Okay, so that looks like this. This is rule 12. I didn't write some of these because I already explained them, and I don't know. It would just be rewriting things that I've already explained. Like exhaustive events, right? Exhaustive events form partitions, and then uniform probability with the six-sided die. Every face has a same chance of happening. Percentage, proportion, probability, they all mean the same thing, but this one, for events A1, A2, all the way to A sub n, the probability of the union of all of these events is less than or equal to the summation of the probabilities. Now, I'll be totally honest, I'm not exactly sure how to explain this. If you combine all of the probabilities of events, that probability will still be less than the sum of the probabilities. I guess like that. And they can only be equal if the events are mutually exclusive. So I think this will actually show up in a problem. I hope it does anyway. But again, these are just rules. A lot of the time with rules in math, you kind of just have to accept them. I mean, some of these I was able to explain. This one, the way I just explained it, I think would be the way to explain it. So I hope it made sense. Like I said, this is also kind of just, the more I talk about it, I think the more it like sticks in my head. So yeah, I think with this I just have to like accept it also. But okay, I'm gonna do some problems, but they're gonna be in a separate video, so that way this video isn't very long. But there are 3 problems. So like I said, those will be in the next video. Okay, I hope this helped. Thank you.